So Lukasz Szpruch is at the University of Edinburgh. He's also at the Alan Turing Institute in London. Before that, he was at the University of Oxford, and he obtained his PhD from the University of Strathclyde in London. And I believe it's fair to say that he is coming from the stochastics community. So it is my great pleasure to welcome him to talk about mean-field neural ODEs via relaxed optimal control today in the first talk of the thematic day on continuous ResNets. And if you've not been to one of these days before, I would ask you, if you've got questions, to post them into the chat, and then somebody will either answer them in the chat. I believe one of Lukasz's co-authors may be in the chat, and otherwise they will be given to the speaker in a bunch during the talk. And there will be possibly a little bit of time for free questions at the end of the talk. And we've got 2 more talks coming up after that. And thank you so much, Lukasz.
Thanks, Stephen, for the invitation. Sorry, how much time do I have?
You've got 50 minutes plus time for questions. And I'm aware that we're starting a few minutes late, so everything is just migrating 5 minutes to the back.
I apologize for joining the last minute. I mixed things up in my calendar.
No problem. My mistake.
So this might be a slightly longer presentation, but of the talk that I already gave before. So let me start. Okay. So thanks a lot for for having me. It's a great pleasure to present this work. So this is a joint project with David Shishka, who is also in Edinburgh, Jean-François Jabir, also from Edinburgh, and Kaiton, who is in Jiren. So this work is motivated by our desire to understand how the deep learning works using continuous time and mean-field perspective. So I will start with a story of one hidden layer, and then I'll show you how this can be translated or extended to the Neural ODE setup, which is a prototype for the ResNet neural networks. So I'll start with the key messages that I'll try to convey today. So one thing that I'd like to persuade you to today, if you're not already seeing that way, is that sampling, when we're optimizing these neural networks, we should be thinking about sampling rather than actually optimization. The reason for that is that we're using stochastic gradient algorithms to train those neural networks. These are stochastic processes that generate probability distribution function over the parameter space. And what we're trying to do is to find some optimal distribution of a parameter space of the neural networks, rather than finding one optimal set of parameters. And so particularly helpful perspective here is to use the Wasserstein gradient flow perspective that I'll try to walk you through today. And once you do that, then typically you'll develop analysis in a little bit abstract setup. And then you can discretize this using probabilistic numerical analysis methods that often give you access to dimension independent bounds of convergence in terms of all the parameters that you're interested. Okay, so definition of the neural network, I'll perhaps skip, everyone knows that. So like I said, this was the talk that I was giving some time ago. So I'll jump here. For those who haven't seen that, this is taken from the paper by Belkin from PNAS, but a few other people that made that observation. So what's interesting about the neural networks, well, I find it interesting, and it's to some extent new, is this double descent picture. So what we have here on the x-axis, we have complexity of the model, which is roughly proportional to the number of parameters that we're trying to train. And on the y-axis, we see risk, so that would be a generalization error. So, you know, one-on-one statistics that we teach students, we see that left-hand side of that picture. That basically means that if you take too few parameters in your model, then typically with respect to the data points, then you cannot, you don't expect that you can generalize well. If you take too many parameters, you overfit, and you also don't generalize. And there is classical statistical learning theory tells us that there is a sweet point between number of parameters that we take in our model that we train. And so that's kind of a picture we had in mind in the era pre deep neural networks or over parameterized models. But what people observed well, empirically and slowly, there is some theory that backs this up in certain regimes, is that actually what happens for those neural networks is that you have a number of parameters that often exceeds the number of data points that you train. So that sounds crazy. And then you use stochastic gradient descent to train them. And that stochastic gradient descent selects parameters of your neural network so that your generalization error improves as the number of parameters increases. And so there's, like I said, there is still not a full theory explaining that, by kind of possible explanations as I'll be using this noisy stochastic gradient descent that regularizes our problem. And if we choose those larger models with a large number of parameters, then this makes it somehow a bit easier for the stochastic gradient descent to identify, to find good local minimum, whatever that means, okay? So that motivates also a little bit why it is helpful to look at the, or might be useful to look at this hugely over parameterized setup. Okay. So because the work, we first wrote a paper on the one hidden layer, and then we extended it to this neural ODE. So I'll start with one hidden layer. And then the story is fairly similar. So this is the setup that has been studied by Andrea Montanari and Francis Bach and Lenaik Tizat. So on the left-hand side, we have the this rescale neural network where phi is my activation function and beta and alpha are my weights. And we use this rescaling of 1/n, the so-called mean-field scaling. And so in this setting, what we can observe that the neural network becomes a linear function of measure over the parameter space, okay? And so with some extra notation that if I want to hide the parameters, I have a phi hat, and x denotes the parameters alpha and beta, I can write down a classical supervised learning problem for input data z and output, for input output measure nu, where z corresponds here to inputs that my neural networks and y to the outputs. I can solve this supervised learning problem where this, you can think that this is square for simplicity. So what we do, we take expected value with respect to the data. Possibly we add some regularizer that here we decided to take as x squared. So remember, x is the parameters. And so then we have a function fx plus sigma bar square over 2 times this ux here as x squared. And we try to minimize with respect to x. So of course, the problem is that this is a non-convex function in x, in the parameters. So if we would like to just use naive standard gradient descent with some learning rate tau written here, then there is no hope because, at best, we will be able to find a local minimizer. And so we should not expect that that method will give us good results in general, okay? Or find a global minima if such exists. So the idea here is that we want to study slightly idealized version of that stochastic gradient descent. So we say, okay, in practice, you won't be able to access the full gradient. We will be approximating this with the taking mini batches in data, or we might be using some dropout argument, and each step of the algorithm only training some parts of the neural network. So here, for the mathematical convenience, we take very simplistic version that we add to our deterministic gradient algorithm. We add some Gaussian perturbation, saying you can think about this as a perturbation to the gradient. For the full theory, it would be interesting to consider sigma that is state dependent, but now for simplicity, we are only considering additive noise. Okay, so you add this noisy or perturb gradient descent algorithm, and then you can observe that, well, this is nothing but Euler approximation for a stochastic differential equation written here. And so if you look at that stochastic differential equation, which is now a continuous time noisy gradient descent for training one hidden layer neural network, you observe that you naturally landed on something which is called in literature interacting particle system. That is, for each particle I, each particle I interacts with all other particles in the system through empirical law. Okay, so these things have been studied in statistical physics, limits of interacting particle systems leading to Markov-Vlasov equations that I will tell you in a moment. But here is just, you know, the sketches of derivation. We started with this rescale one hidden neural network. We apply noisy gradient descent. We and now we're considering continuous limit of that for the analysis. This is not necessary. This could be all analyzed at discrete time, but it's just a little bit easier to work in a continuous time. So once you have this equation and you're saying, okay, if that stochastic differential equations now mimics this noisy gradient descent, and you can ask the question, so what happens to the law that this process induces when time goes to infinity? You can ask the question, does it converge to some stationary, that law induced by that process converges to the stationary distribution? And if it does, what's the relationship of that stationary distribution to the original problem that we were trying to solve? So when you look at that equation, and what we were aiming in this one hidden layer network paper is we wanted to understand that question for any sigma. For sufficiently large sigma, you can see that I would be able to get some contractional motonicity, as we will see in a moment, that I will assume from this regularization term, not worrying too much what I'm getting from the network. But for arbitrary small sigma, the question of existence of invariant measure for this interacting particle systems are highly non-trivial. People have been studying this for the last 30 years, and I think we're kind of reaching the point where we have fairly optimal conditions. Okay, so rewrite. So this is my prototype for one hidden neural network. Now in this mean field setup, I can recast my problem of supervised learning from minimization over parameters to the minimization over measures, because now I'm looking at the measures over the parameter space. So I view this as a function of the measure. And the observation that, like I said, has been made by Andrea Montanari and then a few other people, that function is convex in a usual sense. When we're talking about functions of measures, they different notions of convexity. So this is a classical convexity. There's also displacement convexity, which is more related to the optimal transport. So here is just a basic convexity. And so the question is how to exploit that. So again, with a little bit of rewriting, note that that original loss function that we were considering, viewed as a function of a measure or empirical measure, if I wanted to, if I could rewrite now my particle system in with this extra notation in the following way. So that was this interacting particle system that we derived from sort of first principles. And now I would like to send n, so number of neurons in my network, to infinity. And once I do that, we can prove that we converge to Makin loss of stochastic differential equations. And you can study those convergence rates. In some regimes, these results are quite well known. In some other regimes, a little bit less. I'm happy to comment on that. I spend a good chunk of my life studying this kind of things. And so the one thing that I would need to explain, and I hope that I have this on my slides, is what I mean by this dm. So this is a measure derivative. The community I'm coming from, which is this combination of stochastic analysis and stochastic control, we call it a Lyon's derivative, as this was derivative that Pierre-Louis Lyon proposed when studying a problem on mean-field games. However, this is also the derivative that has been used before by people working on gradient float and optimal transport, so-called metric derivative, developed, initially idea put forward by Otto and then further developed by Ambroise, Gilly, and Savarin in the beautiful book. But you have a function of measure, and now you're applying a gradient descent, and the same principle, you take minus the derivative, and the only difference is that because you're minimizing a function of a measure, you take derivative in the measure. So I just, what this derivative is, for those who are not familiar. So there's a couple of different notions of taking derivatives with respect to the measure. So here, the ones we are using is so-called a functional derivative or flat derivative. That this is the most classical you can think about as a Gatto derivative. So if you have a function of a measure, how you define this derivative? You take a convex combinations of your measures. So and you send S to 0, and if that converges to the object like this, then you call this delta V over delta M, your flat derivative, and you know that that derivative is only defined up to normalizing constant. So if you add a constant to this, you integrate of a difference of two measures, and therefore that will be 0, right? So this is only, so as a convention, typically you will take that, this is 0. In contrast, this intrinsic Lyon's Wasserstein derivative, like I said, this is a topic that has been studied a lot recently due to the development of theory of mean-field games, that lots of new people started looking at those notions. So again, there's a couple of different ways to define those derivatives, but the ones that is perhaps the most intuitive, and at least it looks very similar to the way you define a classical derivative, is that you take some vector field, phi, and then you transport your measure along that vector field. And if you now send S perturbation to 0, then what you get here, if that limit exists, what you get here is your Lyon's derivative or intrinsic or Wasserstein derivative product with your vector field. So a little bit of intuition. If you take a linear function of the measure, then if you your flat derivative of that linear function of measure is just f. However, the Lyon's derivative of this guy is a gradient of f. Okay, so that's how you can link, and it turns out that that relationship in generally holds. So this is how those two notions of derivatives can be linked. Okay, so this is a little bit of the background in theory that I think this is helpful. So the perspective that we are taking in this work is the, like I said, you know, at first, by looking at this equation at the bottom of the slide, we've seen that this was this Mean-Field Langevin dynamics that we derived as a limit, mean-field limit of the noisy stochastic gradient. But there is also a variational perspective that is very helpful. So remember that f of m, that was our loss function for the supervised learning that we're optimizing now over the measure of a parameter space. And we add to that the regularizer. That regularizer is an entropy defined here. So this is Kullback-Leibler divergence between your measure m, measure on the parameter space, and some Gibbs measure g with the potential u. Okay. So it turns out that if you you won't have this variational perspective, that this is a gradient flow that minimizes this energy function. And so maybe a couple of comments. So we, if we just had regularizer, which would be relative entropy with respect to the Lebesgue measure, then we wouldn't have that term u. And why we're working with it is there have been a couple of observations made in literature. So one is that, as you will see, this could be thought of in the context of Bayesian neural networks, of putting a prior on your weights, which is the prior being your GX, your Gibbs measure. There have been recently a paper by Maxim Raginsky who observed that for sigma sufficiently large, this could be also seen as a gradient flow for the lazy training. That is, you know, your measure do not go too far from Gaussian, or it's not changing. So this framework encapsulates quite a few different perspectives that people recently had in that literature. So a couple of assumptions. So we, like I said, we assume that f is a convex function, and we assume that u is dissipative and that the gradient is Lipschitz continuous. You can have some more general assumptions here, but that was not the point of that work. So the first result that we have is that f is a assuming that f is continuous in the topology of reconvergence, then the sequence of functions v sigma, so that was, remember, loss function plus regularizer convergence in the sense of gamma convergence to f as sigma, which is regularizer, goes to 0. So that means that if you have unregularized cost function f evaluated at m, so m is now this optimal minimizer of this v sigma. If you send take lim sup by sending regularizer to 0, you converge to the minimum of the original function that you are trying to optimize. But sadly, you don't have a rate of convergence here. You could get some rate in terms of by getting bounds on the entropy, but this would be dimension dependent and not particularly insightful. So I skip the elements of the proof. So, so under the assumptions that we are working, we are able to characterize a minimizer of our function v sigma. So remember, v sigma is this loss function f plus a regularizer. So if the function v sigma has a unique minimizer that we denote by m star, which is absolutely continuous with respect to the Lebesgue measure, then it satisfies the so-called first order condition. So what this guy is the, if you recall this notion of, we had two notions of taking derivative, the flat and intrinsic. This is to say that this is your flat derivative. If I go back here, this is the flat derivative of this energy function here that we're minimizing, okay? So this is your function f, and this two bits are result of taking a flat derivative with respect to the relative entropy. So this guy should be constant. Remember that flat derivative is defined only up to a constant. So you could say that if you would, and you remember the link between flat derivative and Wasserstein derivative is that the Wasserstein derivative is a gradient of a flat derivative. So that means that gradient of this guy is equal to 0. So that tells you that then this intrinsic derivative is equal to 0 will give you an alternative way of writing this first order condition. So from here, you immediately see that you can write explicitly the form of the optimizer M star, which I hope I have written on the slide. That is, you know that this needs to be constant. It happens to be actually normalizing constant. And then you can write an equation for M star, which will be now the Gibbs measure expressed in terms of your loss function. So that will tell you this optimal, the characterization of the optimal measure that your stochastic gradient converges to. So, okay.
Lukasz, there is a question in the chat saying, how is U chosen in practice and how much does it affect the performance?
So at the moment, U is only assumed to have this dissipativity property. And we need that actually to establish the convergence. So what you will be able to show, what we'll be able to show, as we will see, if this sigma is sufficiently large, we will be able to exploit this dissipativity property from U to prove exponential convergence of the stochastic gradient descent to the optimal measure. And for sufficiently small sigma, we are not able to get convergence rate, and the choice of U is here that only we need that a little bit of this dissipation. Okay?
Thank you.
Right, so connection here to the of this gradient flow. So on the previous slide, we had this result that we established we characterize the minimizer of this cost function in terms of the first order condition, which is written here. So like I said, I mainly work with the SDs, but of course there is for every SD, there is a corresponding PDE. So you can see here that if I have this condition being equal constants and you formally apply gradient, multiply by M star and apply the divergence operator, then you will see that this condition gives you a characterization of the a stationary solution to the corresponding PDE. So that PDE, this M guy, is a law of my parameter space, and this is a law induced by my noisy mean-field stochastic Langevin diffusion. And that M star, as I said, you can get from this first order condition equal constant, you have logarithm here, so you can explicitly compute this guy. This is, however, note that this M star is an equation, so I have M star on the left-hand side and I'm M star here on the right-hand side. And so you have it, and so you see from here that if you add this entropy, then your optimal measure, you can write it down as a Gibbs measure. And so then what you see that the stochastic gradient descent, this noisy stochastic gradient, is just an algorithm to sample from that distribution. Okay? And so that's why what I said at the very beginning of my presentation, that one message that I'll try to convey is that when we train neural network with sampling rather than optimizing. So mathematically now we have a pretty well defined question. We have Mean-Field Langevin equation given here. We have corresponding Fokker-Planck for its law, and we would like to study the convergence of this guy to the invariant measure. So first of all, we would like to understand whether we have characterization of the optimal solution m star of the function that we want to minimize. So we would like to now understand when this law, so mt is the law of xt, converges to that invariant measure m star that we just identified. So under what condition that's true, and potentially under what condition we can get some convergence rate for that. And so it turns out that this is a fairly challenging question. And the study of the invariant measures for this Mean-Field Langevin equations are by far non-trivial. And so this question has been studied a lot by work of Carrillo, McCann, Villani, Otto, Julian Tougault. Typically, as this literature originated from statistical physics, that meant that functions that drive the functions of measures that have been studied here were linear functions of measures, and they were having a specific structure. So in particular, if you go to work by Villani, you will see that there's lots of work about the convergence to the invariant measure of this Mean-Field Langevin equations, but often assuming quite structural conditions on the part of the drift of this equation that depends on the measure. And the other thing that we're trying to get here, we're trying to get that convergence for arbitrary small sigma, because remember we were after this result that will allow us to study the limit, what happens to this noisy perturbed stochastic gradient if we send noise to 0, okay? So none of the results from literature applied. So let me walk you through what we were able to show. So we have this intrinsic, like I said, this derivative. So here we assume that we have some regularity of this. So we have regularity in X and regularity with respect to the Wasserstein 2 distance. And so the key result is to show that so-called dissipation of energy. So recall that V sigma was a loss function, regularized loss function. So we are interested what happens to our loss function or energy function as time goes forward in my stochastic gradient. So MT was the low distribution of a parameter space. And so we see that the loss function is decreasing because we have minus here and we have this guy squared. And so this is the what typically you get in the when you apply gradient type methods to your loss function, that you get this precise property that your energy or your loss function is decreasing along the gradient flow, and we were able to get this here. Mathematically, a challenging, perhaps slightly challenging thing is that we note that this result requires to apply a chain rule for measures, and entropy being only lower semi-continuous function is not immediate that chain rule here holds. But with a little bit of the regularity assumptions that we were able to establish, we've managed to say that it works. So that's a technical contribution of that work. And one of the, again, on the mathematical and more interesting result that we've managed to establish is to prove convergence of the law of my stochastic gradient descent, so that was MT, to that optimal invariant measure M star as times go to infinity. So to establish this result for arbitrary sigma, we had to develop a fairly new technique by combining some dynamical perspective and LaSalle principle together with some Malavian calculus estimates on the density. So that was a technical part of work, and we think that this is of independent interest. And like I said, with the extra assumptions, sorry for the question marks, with the extra assumptions, so let me skip all the details, but remember sigma square was the regularized, this parameter telling us how much we regularized the problem. So if the sigma is sufficiently large, so note that all these terms are positive and this guy is negative. If that regularization is sufficiently large, that what we're able to get is the exponential convergence. So if you want to think about this, this result that is similar, so what people have been recently getting excited about in this kernel limits, or as Francis Bach and Lenai Tizat call it, lazy training. That so in this lazy training, you show that your parameters of the neural network or your distribution of the neural network is not changing much from the initialization, and in that setup you can prove exponential convergence. And here we kind of approach the same results from slightly different perspective. We say, look, you add this regularizer with respect to that Gibbs measure, which you can think of as your prior that you're putting at the initial distribution on your weights. And then if that regularization is big enough, that is, you're not deviating, your posterior distribution of a parameter space of your neural network is not deviating much from that prior, then you get exponential convergence. So perhaps that slightly generalizes this ideas of lazy training. And so then finally you want to say, okay, you've developed some mathematical results for the continuous time and this mean field limit with infinitely many parameters. Is that interesting? So the perspective that we want to take is very much in this I think the spirit that Wei and Yi has been doing research and advocating for the last few years, is that it's helpful to look at those objects coming from machine learning community in the more abstract setup, and then look at use probabilistic numerical analysis to discretize them. So that's what we do here. So if our loss function is sufficiently irregular, and that regularity that we define here is with respect to taking those flat functional derivatives with respect to the measures of first variation, if you like, that's I think another name that people use in literature. And you have your M star, which is a minimizer. Then what you can show is that f of M star, which is the optimal M being this minimizer, minus f of the empirical law. So the empirical law is a finite number of neurons. So remember, n does corresponds to the number of neurons in this one hidden layer network. Take infimum over this, and you can show that that error is within 2L, which was this bound here, over n. And so this is a static result that one could write a corresponding dynamic result that this 1 over n could also be obtained on the level of a stochastic gradient under some regularity conditions. We're working on that. So that shows you that working with this abstract measures actually is useful, because you have a very precise quantitative estimates telling you what error are you making by taking that approximation. Okay, so this was one hidden layer, and how this extends to the neural ODEs, i.e. residual networks. A quick example here. So this is our starting point, and this is very much, like I said, the paper by Wei and Yi was the first to observe and link, to my knowledge, residual networks with dynamical systems. So if you take this as a prototype model for recurrent neural network, where X here is your state and theta are your parameters, then you can see that you can view that again as a discretization of ODE. You know, you can be interested in studying that from a mathematical perspective, because maybe it's easier to work with continuous time, or you might be interested in a situation what happens to those deep neural networks as number of layers goes to infinity, or perhaps you are interested in fitting continuous time data with a neural network, and actually using language of ODEs is very natural. So wherever you come from, so the same setup, I have now xt, which corresponds to the output of my neural network at layer, if you like, or terminal time t, with input xi. You take mean square loss, you integrate with respect to your input output measure, and you want to take derivative with respect to parameters of your neural network. So in this continuous setup, the parameters, of course, are is a process that continues, parameterized by t. So you do what you do. You take you perturb your parameters in some direction, theta tilde. You do that little computation of taking derivative. Then you observe that if you take derivative of your x process with respect to the theta, then that solves linear ordinary differential equations, which you can solve. It has exponential form, and you plug everything together. It's a little bit ugly, sorry. But the point is that you see you have this was a loss function. We take a derivative with respect to the parameters. We have that monstrosity here, and we have the difference between theta star and theta t. So we have a parameters at theta t, and you're asking the question in which direction I should do perturbation of my parameters, how I should perturb my parameters so that I'm minimizing my loss function. Well, you see that if I take this difference to have this form, so that I have minus something squared, the same as we had for one hidden layer, then that my energy, my loss function will be decreasing. So this is you know, a quick example that you can persuade yourself how to take this derivative, even though now for those ODEs, the functions that this neural ODE is not a linear function of the measure. It's a non-linear function of the measure. Nonetheless, a similar principle applies. And one observation that you make is that that pretty ugly gradient of x can be actually rewritten as a solution to the backward ordinary differential equation. So this is this part of your cost function. So you start with a terminal condition given by this guy, and then you solve this backward equation. So this is called a maximum principle, or Pontryagin maximum principle. Again, Wei and Yi was the first one to make a connection between this maximum principle and the training of deep neural networks. And Pontryagin was so that when you work on control problems, there are kind of two schools: Bellman and Hamilton-Bellman equations, and then Pontryagin maximum principle. Advantage here potentially is by using this backward equation is that you don't need to compute derivatives forward of your process x, which are here. Oops, that might be expensive if you have lots of parameters and your state space x is large, and you would need to compute large matrices. Right, anyway, so this was the example, and then if you see that, you can now extend that work that we had before. So again, we consider data and measure of a data space. We work in a setup of what is called in control theory relaxed controls, i.e. we view controls, i.e. measure on a parameter space in that interpretation of working with neural networks to denote nu, that we denoted by nu, and then we consider a dynamic of the following form. So psi is initial conditional input, if you like, to your neural network, and then you controlling your dynamics with measure nu. So this is the link, as you know from the first part of the talk, we'll be now aiming, what's the optimal nu? Is there some invariant measure? Is there dynamics or gradient flow for that nu, and then invariant measure for this that minimizes my cost function? So it turns out yes. Another motivation why you might want to work with those relaxed controls is there's actually quite a lot of work in reinforcement learning, and there you always work with policies which are so-called stochastic or randomized, which is a different ways for saying relax. That is distributions. Okay, so now what I have is we take a cost function as before. So I have this g, which is a terminal cost. So you can think about this as, for example, g might be equal x squared, in which case this would be mean square supervised loss between output of your neural net and the data. And here you have extra, because we take this control perspective, we consider the cost function f. You can think about this as a regularizer, or you can, like I said, you just you might be thinking about bringing perspectives from this training neural networks by using stochastic gradient descent to solve control problems. So depending which perspective we like both perspectives, using control perspective to help understand deep learning, but also bring tools from machine learning and try to devise new algorithms for solving high-dimensional stochastic data-driven adaptive control problems. So as before, we have now nu, which corresponds to the measure of a parameter space of the neural network, if that's my interpretation of that control of my neural ODE. And so the gradient flow, as before, I was writing this as the PD, depending what you like. In more concise way, I'm considering a PD in divergence form with some vector field B. So note here that we have two time indices S and T. So T corresponds here to the, it's a parametrization of this PD. It corresponds to the slice of the distribution of my control at time T for my ODE process, or i.e. layer of my neural network. And S is now the time of the, along which my gradient flow progresses. And so as before, I have this regularized loss, J sigma, and I want to find B, I want to find the gradient, vector field of my gradient flow such that I'm decreasing my loss function. So like I said, we are using this Pontryagin maximum principle framework. So a little bit of notation. We introduce a Hamiltonian. So Hamiltonian h little h is defined as your drift coefficient of your RDE times the placeholder for the gradient plus the cost function in your cost function J. And the capital H is we integrate Hamiltonian with respect to the measure. So this will be measure of the controls, and as before we regularize with entropy, and this is relative entropy with respect to this Gibbs measure as before. And so we can write the adjoint process, which I show you that in the simple example naturally appears in that context. And so, skip assumptions. And so then what you can prove, which is fairly classical result here, maybe a little bit slightly more general because we work with those measures. That's why we proved it from scratch, is that if nu, that is your control, is locally optimal, then it must solve the following system. So you have your forward process that depends on you. Then you have your backward propagation, this adjoint process P, and then your new need to be a minimizer of the regularized Hamiltonian. This just gives you characterization of the optimal solution, locally optimal solution to your control problem, i.e. minimization problem for your neural network. And as before, where we had that chain rule for measures, we can do that here as well. It's a little bit slightly more involved, but philosophy is the same, is that I have my cost function and I compute the derivative in time over my gradient flow. And we compute this and we get this guy. So remember, at the moment we are working with some arbitrary gradient flow that is driven by this vector field B. And so the question is how to choose this B so that my cost loss function is decreasing along the direction of the gradient flow. And so, you know, you see what this B should be. It should be nothing but this gradient of A flat derivative of H, which was your Lyon's derivative of the Hamiltonian. Oops. And so you make that guess, and what we have here is now this gradient flow with a vector field B of this form chosen so that I'm decreasing the energy, and then I wrote a stochastic differential equation that is the stochastic gradient on this noisy gradient descent that we're using to minimize this Hamiltonian. Okay, so then this is your again Mean-Field now Langevin equation. Mu st is your law of the induced by this process, and your forward backward system is given here, right? So if you were want to implement this, what this tells you, you know, you start with some you discretize this dynamics of your gradient flow, and then what you do, you discretize all of this, and then you move forward as you do in the training. Then adjoint process carries the information about the derivatives of your cost function. This is your backward process, and then you update your parameters in your gradient descent, and you make one step of the gradient descent. So again, there was a paper in Journal of Machine Learning by Wei and Yi that he made the suggestion that that's one algorithm that could be used. And so here, in this context of measures, we prove convergence of this algorithm. So the assumptions, so here we are working in the simplified regularized setup where we will get exponential convergence, and I skip that setup that for arbitrary sigma we can have a convergence as well. We can do that without any problem where we don't have convergence. The metric that we work with, but it's not quite a metric, it's pseudometric, that is this integrated Wasserstein. So this is a standard Wasserstein between two measures, and we integrate over time as we work now with controls that are distributions on the path space. And so you could think about that what we're doing is considering gradient flow with respect to that metric. We can put 1 over t here if we want this to be satisfy triangle inequality. And so theorem is that, well, first there is a minimizer. 2, we can characterize minimizer in the same way as before. So this is this bold H is flat derivative of the Hamiltonian, and this guy's are as before. And if my sigma is sufficiently large, then oh yeah, I have definition of this bold H. Then we have exponential convergence, and as before, you know, from that first order condition, I can write down an equation for the Gibbs measure, and then see that my noisy gradient descent, or my Mean-Field Langevin equation that I'm using, is sampling that is converging to that optimal Gibbs distribution that we derived. Okay, almost there. So now again, similar as before, everything in a continuous infinite number of parameters and continuous time, and can we now use language of probabilistic numerical analysis to go down, discretize everything? It turns out we can. So N2 here corresponds to number of parameters, as proxy for number of parameters in neural network. So I consider the particle system for my parameters. And then what we can get is we can get a convergence. And one here is also, we are approximating a measure. So this will be now empirical measure, so that we have N1. N1 is the size of a training set. And so we can get a convergence of my particle system and quantify the uniform mean time. We can discretize it with time, as you do, and then again you can get a classical discretization error. You could have different discretization methods and get different rates. This whole industry of methods around that. And so then what we could say about generalization error, or at least attempt of saying something about generalization error. So recall that the cost function that we were minimizing is of this form. So this is the a running cost, terminal condition, and this regularizer. In practice, of course, we have finite a number of data that we train, and note that what happens in machine learning community, so the engineers machine learning community, is that the cost function that is being considered is only this first part without entropy, of course. Then in practice, you never run vanilla gradient descent on this. You always use some randomization, perhaps not the one that you add additive noise, but like I said, you use dropout, you use mini batches, you use tons of different tricks, which in effect induce noise. So that means that you could, from the gradient flow perspective, you could see that your cost function, that noisy gradient descent, some version of gradient descent that you're proposing, is in fact minimizing a modified cost function. But then at the training, what you do, you still measure your error, how well you train, using original cost function. So what happens here is that, like I said, you start with original cost function, then you propose some modification of gradient that would minimize that cost function, which means that effectively perhaps you're minimizing slightly different function, but then you still measure the error with original cost function at the training. And so this is what we're saying, this entropy term could be viewed as this effect of this implicit regularization. And okay, and the result that we have is that we can quantify all those errors. Now this is my cost function with M, so that is full measure, population measure, at the optimal new star, that invariant measure of regularized problem. This is now a cost function of my optimal measure of regularized problem that I have N1 data points that I've trained, N2 proxy for number of parameters of a neural network, delta S with a time step of my gradient descent. And we can quantify all those errors quite precisely. And then generalization error, or one way of writing generalization error, so that is, so this is the guy that all algorithm spits out, and then I'm looking at my cost function at population measure. So I can decompose this error into this first term, which I perfectly can quantify here, and entropy. So how far, we've measured by using entropy, is my new star, this invariant measure from my Gibbs measure, so my prior, and the best I could have done for this problem. So so you see that this is quite interesting that I have this, if I had a good prior, then this will be small, and you know, there have been some similar flavor results by trying to estimate the generalization error using information theory.
Lucas?
Yep.
Just a quick note, you've got about 5 minutes, including questions.
Yes, I'm done. And so the last thing, food for thought, is that what we remember what I told you is that the in practice, typically you stop training when your cost function, as measured with, of course, empirical data, because that's what you have access to, is less than some error tolerance that you set. And so if you do that, so this is assumption that would need to be proved, how this epsilon depends on all the parameters and when this is achieved, then in principle, that would give you a way to quantify a generalization error. But at the moment, this is assumption and this is future work. Okay, so I'm done. Thank you.
Thank you so much, Lucas. We've got maybe room for one question. Does anybody have anything they want to ask urgently? Otherwise, we can ask questions in the chat, and possibly, I don't know if you're here at the end of the event. I know that it's late in Europe, but definitely in the chat, there should be a little bit of time. If nobody wants to unmute themselves right now, I've got a question. Namely, I think you proved this convergence to an invariant measure, and I think your initial condition does not matter. Is that correct?
That's correct. Yeah, we have that result independently.
So but obviously in practice you've got finitely many particles. Do you have any? Does this tell you any intuition of how you should initialize your system, or how many particles you need for this, or is it a purely continuum result?
No, so we had well, a couple of things, right? So when I told you that there is that perspective of using Bayesian neural networks that keeps measure that you put there is your you could think about initialization is your prior that you put on the neural net. And then, you know, if your regularization parameter is quite high, you have this exponential convergence independent of the initial condition. And you can quantify all the errors in terms of number of parameters. So then, you know, you could say that if that gives you some guidance how to choose number of parameters, yes, you know, because you have some rate, you have some other error coming from a number of particles, and then you can try to make them, you know, kind of the same order. If you're in the regime that sigma regularization parameter is very small, then you don't have that convergence rate, and then we don't know.
Thank you.
Theorem 4, let me have a look. What was the theorem 4? So the papers, if you go to mine or David Shishko's webpage, yeah, okay. So the theorem 4 is it's in a paper on one hidden layer neural network with David Shishka, Kaitong Hu, and Zhenji Ren. And for people interested in the analysis, weak propagation of error, weak propagation of chaos, quantitative analysis for functions of measures, I wrote a paper with my for my PhD student Alvin Se and Jean-Francois Chazanyu. Is on my website. It's called the quantitative propagation of chaos via measure calculus. I can send a reference.
Thank you so much. And I think, thank you again for giving this wonderful talk. And I think it's time for our next speaker.
Hi,